Transient analysis. Transients are generated in electrical circuits having energy storage elements like inductors or capacitors when sudden changes occur in the operating conditions. This occurs when the circuit is powered up for the first time. A first-order circuit has a single energy storage element, for example, either a capacitor or an inductor. A second-order circuit has two storage elements, for example, an inductor and a capacitor. RC circuit transient analysis. Consider the circuit shown in figure 1 below. It's got a voltage source, it's got a resistor with R ohms, it's got a capacitor with C farads. There's a current IT flowing and the voltage drop across the resistor is VRT and the voltage drop uh, about the capacitor is VCT. Using Kirchhoff's voltage law KVL, which states the voltage around a loop equals the sum of every voltage drop in the same loop. Referring to figure 1, it can be said V is equal to VRT plus VCT, which gives us equation 1. Now for a capacitor, we know that VCT is equal to 1 over C and the integral of IT dt or dVC dt is equal to 1 over C times I, or 1 over CIT is equal to dVC T dt, and IT is equal to C dVC T dt, which gives us equation 2. So in this circuit, the current that flows through capacitor C also flows through resistor R. So VRT is equal to R times IT, or VR is equal to RC times dVCT dt. Now, equation, all we did here is we replaced that IT CdV CdT of equation 2 with that IT. So equation 1 can be rewritten as V equals, and then instead of the VR in equation 1, we write this RC dV CT dt plus VCT. RC is RC in brackets dV CT dt is equal to V minus VCT. So RC dV CT is equal to V minus VCT dt. RC dV CT divided by, in brackets, V minus VCT is equal to dt. Or we can say minus RC ln V minus VCT is equal to T plus K, which gives us equation 3. Now, to determine K, a starting condition must be considered. Initially, the switch is open and the voltage across the capacitor is 0. Thus, at t equals 0, VCT is equal to 0. Replacing these values in equation 3, it can be said that minus RC ln V is equal to K, or K is equal to minus RC ln V, which gives us equation 4. Now we substitute the value of K in equation 4 in equation 3. This gives us minus RC ln V minus VCT is equal to T minus RC ln V, or we can say RC ln V minus VCT plus RC ln V is equal to T. We only took this minus and we transferred it to the left side of the equation. So we can say minus RC ln V minus VCT minus ln V is equal to T, and that can be rewritten as by dividing both sides with minus RC, we get then ln V minus VCT minus ln V is equal to minus TRC, or we can say ln V minus VCT divided by V is equal to minus TRC. Now, taking the antilog on both sides, V minus VCT divided by V is equal to E minus TRC, or we can say V minus VCT is V with e to the power of minus t divided by RC. Or we can say minus VCT is equal to V e to the power minus t divided by RC minus V. Or we can say VCT is equal to V minus V multiplied by e to the minus TRC. And this can be rewritten as VCT is equal to V 1 minus e to the power of minus t over RC. And this gives equation 5. Equation 5 is the voltage across the capacitor in relation to time. From equation 1, that is V equals VRT plus VCT, it can be said that VRT is equal to V minus VCT, which gives us equation 6. From equation 5, it can be said that VCT is equal to V multiplied by 1 minus V e to the minus TRC, or that VCT is equal to V minus V e to the power minus T over RC. Equation 6 can therefore be rewritten as VRT is equal to V, and we simply substitute that VCT with V minus V e to the power minus TRC, and that gives us VRT is equal to V minus e to the power minus TRC, which gives us equation 7. The current IT can be written as IT over VRT over R, and then we simply replace that VRT with V times e to the power minus T over RC, and then we get, eventually we get IT is equal to V divided by R multiplied by E minus TRC, which gives us equation 8. Okay, so if we do a couple of calculations, the RC time constant, also called tau, or is written with the Greek letter tau, the time constant in seconds of an RC circuit is equal to the product of the circuit resistance in ohms and the circuit capacitance in farads. Tau equal RC seconds. So after one time constant, that's tau times 1 times RC, then in equation 5, if we replace T with RC, and we calculate the voltage after one time constant, we get 0.6321 volt for Vc. And if we look here after one time constant, it seems to be correct. And for Vr, after one time constant, we get 0.367 volt. And that is about more or less what we see over here. And then after five time constants for Vc, we get 0.9933 volts, which is complies more or less with what we got here. And um, uh, the voltage in the resistor after five time constants is 0.0067 volt, which more or less complies with what we have here. Similarly, if we calculate the current after one time constant is 0.3679 VR, and after five time constants it is 0.0067 VR. And if we look at the graph on the next page, it more or less complies with with, with our calculations. Okay, so what we have here is a circuit with an input pulse of 1 volt, with a rise time of 0.01 seconds, uh, fall time of 0.01 seconds. It's on for 5 seconds. The total cycle is 10 seconds, and there's a repetition of 3 pulses. Okay, we have R1 as is 10K and C1 is 100 picofarad. So let's look at the waveforms. Okay, first we measure the input pulse. There's the input pulse. There's the voltage across the capacitor, and as we can see, it resembles what the previous graph we had. Now the voltage across the resistor. There we go. It's just the inverse of the voltage across the capacitor. And now let's take a look at the current in the resistor. And there we are. There's the current in the resistor, more or less what we saw in the previous graphs that we had. It just makes this a bit bigger. So you can have a nice look at it. Yeah, and that's it. We have come to the end of this electric circuit video. Give this video a thumbs up. Click the subscribe button. All the links are in the description below. If you have a question, put it in the comments below. Thank you for watching, and goodbye.